Hello, everyone. Thank you very much. For the seminar, I'm very happy to give a presentation here. So the topic today is fluid displacement in porous media, and we focus on the effects of disorder, grain shape, and wettability. So the content of this presentation basically covers the majority of my PhD study, where I was looking at the joint PhD program between the University of Sydney and the Untitled Wang, Paris Tech in France. So firstly, I'll just give a briefly a background about this multiphase flow problem. So here is an example of multiphase fluids where the red fluid is being injected from the left, pushing or displacing the blue defending phase fluids, where you also see the circular particles within this media. And this has quite a wide range of applications, including the water removal in gas diffusion layers in fuel cells, and also the geosequestration, where the supercritical CO2 can be injected deep underground for long-term storage instead of emitting those CO2s into the atmosphere. And apart from that, there's enhanced oil recovery, where either CO2 or brine can be used to displace the oil in the oil reservoir, such that the overall exploitation, the efficiency of oil, getting oil can be improved. So for this particular problem, there are quite a long time for investigation on this problem. So here shows a phase diagram on the regimes during the displacement process. So basically the fluid properties and flow conditions greatly impact the invasion morphology of this process. So here you can see viscous fingering, where a less viscous fluid is being injected to displace a more viscous fluid, or stable displacement when the invading phase is actually more viscous. And also on the bottom here, when the viscous effect can be neglected, which means that either the injection velocity of the invading phase or the viscosity of the fluids are very small compared with the capillary force, then we have capillary fingering. So at the same time, apart from the these dimensionless parameters, wettability or the contact angle is also proven very important. So you can see here that vertical axis is capillary number and horizontal axis is different contact angles. So you'll see that across different contact angles, the overall invasion morphology is quite different, especially you see here at the low capillary number here, you see very compact displacement at high contact angle. So in this case, the invading phase is wetting to the solid skeleton. Just briefly, relatively recent progress on this problem. So here you see again a phase diagram of radial injection experiment where the invading phase is being injected from the center of these Shelly cells. And you see quite a different displacement patterns at percolation when the invading phase reaches the boundary of this circular domain. And also they reveal that in strong imbibition, where in the case the contact angle is very small, you see that there's a transition of increasing compactness from here to here, and finally reaching a very fingering regime with very low displacement efficiency. So this is due to the 3D corner flow effect. And also people use this idea of calculating what's the viscous force or capillary force to suppress this viscous fingering in gradient porous media, where in the geometry you have a gradient in grain size distribution. So from the bottom you have a very small grains, on the top you have large grains. And so in this case, basically all the capillary forces are suppressing those viscous unstable advancement. So you see here that at low Reynolds number, you see that with a gradient, then the displacement is very compact, whereas without gradient, lambda is equal to 0, then you see viscous fingering. And they conduct quite a lot of simulations to show that phase diagram can be derived based on the pore scale capillary force versus viscous force. And then there's a more practical applications where they use the core from the underground, where they conduct the CT scan. So basically, due to the different attenuations of different properties like oil and brine and solids, they can distinguish what are different phases in the images, constructing a 3D image of how the liquid, how the oil, how the brine, and how the solids distribute in the 3D space. And then they can measure what is the contact angle along the triple line, or the solid 1, solid 2, and the liquid 1, liquid 2, and solid contact line. So they find that there's a correlation between the roughness and contact angles, where greater roughness correlates with lower contact angles. So in this presentation, we'll also tackle a few aspects of these problems. So you see that we're gonna talk about how the roughness of the grain surface influence the displacement process. We also move from the nanometer or micrometer scale to micro to millimeter scale, where we look at the effect of particle shape, where the sharp edge pinning phenomenon is present. And also moving from larger disorder or larger macroscopic scale, we look at the topological disorder, how that influences the displacement process. So I'll present this in a sequence from the right to the bottom to the left. So here, start with the characterization of porous material of the disorder. So here is the work that basically inspires our further improvement on this definition of disorders, where they have a plate and they have several circular holes inside the plate, and they study how this random distribution of these spheres influence the stiffness degradation due to disorder. So here you can notice that if I define those cubes as a squarish cube, and then for the slight movement of all those circular circles, they are still within the cube. So which means that if you calculate what is the local porosity fluctuations, that will be a constant number. But if we instead of using all those square cubes, we use Voronoi diagram, then we can propose a more general definition of disorder, where this disorder index is also sensitive to small fluctuations in terms of the location of all those spheres. So the disorder index is defined by the fluctuations of local porosities. So this phi n is the local porosity within the Voronoi cell, and this phi bar is the average porosity. So this number is basically reflects what's the fluctuations of all those porosities. And then using the Monte Carlo method, we can generate the porous media with different disorder, which is defined, characterized by this disorder index. So for the simulation, we have a constant velocity being injected from the left, the invading phase. And also we have the porosity of 0.67 with a capillary number of 0.0031, and the viscosity ratio is 0.8. So the simulation method we used is the lattice-Boltzmann method. So here I present briefly the collision scheme and also the multi-component method we have used. So the main advantage, just briefly, the lattice-Boltzmann method is that it's quite efficient and it can be massively parallelized. And it's very easy to deal with very complex geometries, especially in porous media, where you have a very different locations of all those particles. So here is the phase diagram of this simulation results. Basically, we have a simulation for different disorder and different contact angles. So see that the red color is basically the invading phase, and the blue colors are the defending phase. So if you look closely, you'll see that from the left top to the bottom right, you'll see more and more defending phase being trapped within this domain. So if you're talking about the oil recovery, the bottom right case is not favored because we don't want many oils remaining in the reservoir. So the qualitative observation in this is that the overall displacement efficiency, which is measure of what is the proportion of defending phase that can be displaced out of the domain, it's less efficient for greater disorder and wettability. And to analyze this problem, we can move into the pore scale. We look at how the local pore, which is the space between the grains, invaded by the invading phase. So different invasion mechanisms has been identified. So we have burst event when the capillary pressure reaches the local maximum, and also the touch event here, where that before this burst event, the meniscus touches the next dry grain, forming two new menisci. And also we have overlap event, where you see that here for two different menisci, they can touch each other and then merge into one large meniscus. So we can calculate explicitly what is the critical capillary pressure for each of these events, and then we choose the minimum as the unstable event, and then we can plot what is the fluctuations in the local capillary resistance, and also we see that quite a strong correlation can be observed between the displacement efficiency and the fluctuations of local capillary pressures. Note that all the points here are the simulations from different disorder and different wettabilities. We see a collapse of curves in this plot. So the other very important parameter is the fluid-fluid interfacial area, where it measures what is the basically potential total energy between all those different phases. So here, the modified interfacial length, basically divided by the width of this channel. Sorry, this is the length of the channel, is a function of K and beta, which previously was only a fitting parameters. And this phi is the porosity of the material, W is the width, and S is the saturation. So to combine the effect of disorder and the wettability, we can introduce a capillary index. And then if we plot this capillary index and see how that correlates with this previously fitted K and beta, we see quite a strong correlation between this beta K and the IC value. So we see that for IC smaller than 0.5, we have quite a strong linear relation here. And after 0.5, you see quite a very low beta number and a high K number. So imagine that you have, for example, very compact displacement. So the invasion front is moving forward, which means that during the displacement, the total interfacial area is always almost approximately constant, and no remaining, no defending fluid is being trapped, which means that the total interfacial length is independent of saturation. It just will a constant number, which means that the beta will be close to zero, and the length is independent on this saturation, which is exactly what we observed in this figure. So we can plot the contour map of IC in the theta and IV map. So here's the contour map, and then we can put this back to this phase diagram we observed. So here is the IC greater than 0.5, IC smaller 0.3, and we see that these different IC values separate this whole domain into separate regions, where we see that more defending phases being trapped at the right bottom, whereas on the left top, we have IC greater than 0.5, we have a very compact displacement. So that's the study on the disorder, where we have showed the very important effect from wettability and disorder. And then we move to the sharp edge pinning phenomenon. So here is just a very practical and experiment where you can put actually more droplet on a coin. So the reason for that is because of the sharp edge local at the corner, then you have a greater apparent contact angle compared with the contact angle that you measure on the perfectly smooth surface. And one of the application or observation rather is that there's a spontaneous unidirectional spreading water phenomenon observed in the plant. So if you put a droplet here on the inner side of this peristome of this plant, it will spontaneously spread outwards. But if you put a droplet on the outside, then it will not go back towards the inner side of this peristome. And the reason for that is exactly the sharp edge pinning phenomenon, where you see that on the left side, the liquid is actually pinned. So it cannot move forwards, but it can only move towards the right direction. So that's a quite interesting work here. So inspired by that, inspired by this work, we firstly moved to very simple system instead of going into porous media. So we think about, again, doing some spontaneous transport of liquid. So here you can see that this is just a plate. So if we cut the plate where we have this groove in this direction described by this function yx, then if we place a droplet onto this surface, you can imagine that along the sharp edge, all the liquid is being pinned, so it cannot spread out. But the droplet, because of the tendency of minimizing the total energy, it wants to expand, so that effectively you are actually squashing this liquid so that it will be pushed towards the positive x direction. So then we can do some analysis on this movement. So we can use force balance by considering the capillary force, the viscous dissipation, the contact angle hysteresis, with consideration of arbitrary shape of this wedge. And then we can conduct experiment once we can manufacture different wedge shapes. So here is the result from the theory derived by basically Newton's second law, considering other forces, and also the theory and also the experiments for different droplet size and the initial starting location. And then we can, based on this theory, we can do some more analysis from an energy perspective to show that if we have a convex shaped wedge, then the total travel distance for this droplet can outperform all the straight wedges. So this becomes more of an optimization problem. And nextly, we can move into the porous media. And then in this time, instead of using the lattice Boltzmann method, we try to extend the existing pore network model method. So briefly, a quick introduction about this model. So it considered the pore scale invasion stabilities, burst, touch, and overlap, as I mentioned before. So for example, take the burst as an example. Depending on the location of the meniscus, the capillary resistance at different location and also the contact angle is different. So this can be explicitly calculated depending on the wettability and the pore geometry. And then this algorithm has been relatively recently extended to consider the viscous effect, and also some other works using different approach to consider the viscous effect, or in the quasi-static regime, they try to consider the corner flow effect, which is a 3D phenomenon. So the advantage of this algorithm is that it's highly efficient. It's able to capture the pore scale invasion mechanisms and can reproduce the microscopic invasion morphology observed in the experiment. But limitation is that up to now, only spherical grains or more of circles in 2D can be simulated. So given the particle shape has been observed to impact the displacement process, and also wide range of contact angle distribution is observed even in chemically homogeneous porous media. So chemically homogeneous meaning the intrinsic contact angle is the same. So this basically means the complex pore geometry and particle shapes will make the effective contact angle different from the intrinsic values. So which means there's need for more general pore network model to study the effect of particle shapes. So our model includes 3 main ingredients. So of course, firstly, we consider the sharp edge pinning effect. And here you have a meniscus moving on an ideal smooth surface. The effective contact angle is equal to the intrinsic one. Whereas if it reaches a corner, then it can be pinned with an upper bound of this contact angle being a function of intrinsic contact angle and the angle of this local sharp corner. And as after reaching that maximum number, the upper bound, it will move forward with the contact angle being in the equal to the intrinsic one. The second ingredient is the pore scale instabilities, as in this paper described. And then the third ingredient is the volume capacity model. So basically, at each invasion event, you can imagine that this liquid, this meniscus will move forward, but at the same time, all the other meniscus will retract a bit. It's just a liquid redistribution within this pore geometry. So we need to consider what's the total liquid that is stored within the meniscus that is being redistributed during this advancement event. So combining all these different ingredients, we can have the pore network model. And here is the typical simulation result, where we have the invasion phase being injected from the center, and then at percolation or at the invading phase reaching the boundary, the simulation stops. So note that we consider the quasi-static regime, where we do not consider viscous effect in this case. And the particle shape, the grain shape, is represented by simple polygons. Heterogeneity is introduced by uniform distribution of grain size, and also we randomly rotate all those grains. And then the simulation is conducted for different grain shapes and wetting conditions. So next slide, I'll show the different invasion morphology at percolation for different particle shapes and contact angles. So at the left bottom, you see very compact displacement. So there's no trapping, but on the right top, you see that's very fingering phenomenon, which is due to the capillary resistance. So there's a transition from here to the top right. So then we can look at the impact of particle shape. So firstly, there's a greater heterogeneity in throat size distribution for more angular grains. We show the both the distribution and also the average noted by the dashed line here. And also the other is the greater pinning capacity at sharper edges. So if we have n is equal to 4, which basically is a square, we see that the effective contact angle distribution widens, and also the average value also increases because of the greater pinning capacity, as we mentioned in the previous equation. The upper bound of unpin is greater. So consequently, we can firstly look at the pressure fluctuation. So here you see that for n is equal to 4, the capillary pressure fluctuates more compared with more spherical grains. And also here's the average and the standard deviation of the capillary pressures during experiments. So here we see that across a wide range of contact angles, always for more angular grains, the fluctuations is greater. So we can also look at the Heinz jump size distribution. So basically, it's the redistribution, the change of liquid redistribution during the invasion process. And in the past experiment, it was observed that it follows a exponential law. So here, which is also what we observed in the simulation in the inset. And also we look at how the contact angle and grain shape influence the beta value, which is regarded as a signature of the displacement process. And finally, we can look at the fractal dimension of this invasion phase. So it's basically a measure of the amount of filling, amount of pores being filled by the invasion phase. So it basically changes from a value from 2 to 1.83, which is also observed in our experiments. We also see that for more angular grains, the blue color, it's generally on the bottom of these three curves, meaning that for the same contact angle, the fractal dimension is lower for more angular grains, meaning that generally there's a earlier transition from compact displacement to capillary fingering. And then here's the recent update on the algorithm, where we extend this algorithm into a more realistic porous material. And here you see that all the blue dots are wetted by the invading phase, all the gray dots are dry surface, and all the black dots are the region that is being trapped. So because of the incompressibility of the defending phase. Once the origin is trapped, it cannot be further invaded. So the other thing to note is, although you see that all the meniscus shape is straight lines here, but actual calculations are based on the actual shape of the meniscus. So the straight lines here is just for simplicity for the demonstration purpose. And you see that on the left, it's a 60 degree, and on the right, it's a 120 more hydrophobic case. So for example, in this region, for more hydrophilic case, the smaller throats are being filled, whereas for 120, there's a greater trapped area inside this area. So and next we look at the roughness. We're moving smaller and smaller in terms of length scale. So this is basically trying to answer the question where there's a conflict between the observations in the literature. So one is that they observe the greater roughness is associated with lower contact angle. And in other works, they found that greater roughness leads to greater contact angle during multiphase displacement process. So we want to look at how does grain roughness influence the effective contact angle. So I'll just move forward quickly. So we consider the wetting models on simple surface where we have Young's model on perfectly smooth surface, or in with the presence of roughness. Depending on the wetting state, it can fill in the grooves, or there can be air being trapped between the solid and liquid. And then there's a different equations describing those different modes of apparent contact angles. So here is the schematic of experimental observation of a droplet. As time goes on, you see the apparent contact angle decreases, which experience a transition from this Casey state to Winslow state. So the transition from Casey to Winslow is a function of many parameters, including geometry and liquid properties. So basically, you want to overcome an energy barrier going from Casey to Winslow. So also from the literature, there's a quite strong overlap between the possible time scale of wetting transition and pore evasion, so that we consider this effect in our simulation. So based on theory, I just quickly, the idea is that you want to have a theory describing the amount of solid liquid contact area, then you can plug it into the modified Casey equation so that you can calculate the evolution of apparent contact angle as a function of time. And then we can express the relative speed of wetting transition compared with local pore invasion in multiphase displacement process by this dimensionless number. So here is how the phi value changes as a function of time, and also what is the apparent contact angle changes with time. So this model can be incorporated into the lattice Boltzmann method, where the contact angle will be a function of time. So the longer it contacts the surface, the smaller the contact angle is. So then here is the simulation results. Again, if we look at the total trapped area, the total trapped defending phase, then we can see that the effect of wetting transition is quite obvious in this figure. You see that for greater dy value, which means slow transition, the more trapping of defending phase can be observed. And here is basically showing the wettability distribution at percolation. So on top, it's basically all the roughness is filled by the invading phase, with several exceptions by the blue colors. And at the bottom, it's a very slow transition, meaning that there are defending phase being trapped in the roughness grooves. So finally, we can look at the different mobilization of different modes. So this is basically translation mode, where one defending phase ganglia moves to another place, fragmentation, one split into two, or coalescence, so multiple merge into one. So here are the statistics of the number of merging or fragmentation events during the whole process. We see that at dy approximately being equal to 6, it reaches the maximum value, which is actually consistent if we also look at the translation. So here, basically all the blue dots plots the average velocity during this translation process. And this red curve shows the summation of the viscous pressure and capillary pressure gradient. So we just demonstrated here that the both viscous and capillary pressure needs to be considered in order to describe how easily trapped ganglia or trapped defending phase can be mobilized. So basically, this work reveals the significant effect of roughness, which leads to the time-dependent behavior of contact angle, which ultimately impact the displacement process. So just a summary, we look at different physical mechanisms at different scales. We study how that influenced the displacement process. And overall, the conclusion is that the intrinsic wettability plus the particle shape and roughness influence the effective contact angle. And then the effective contact angle combined with the pore geometry determines the pore scale instability events. And this finally determines what is the microscopic evasion morphology is. So finally, I would just acknowledge the funding and also the University of Sydney HPC service and many supervisors and collaborators. So that's the end of the presentation. I'm happy to take questions.